This video is about the details of covalent bonding. This is an introduction. As we have subsequent videos in Unit 2 in AP Chemistry, you're going to learn more about the details of how bonding occurs. And the first thing we're going to talk about is covalent bonding. Covalent bonding, you recall, is when electrons are shared between atoms. Sometimes that's equal sharing, sometimes it's unequal sharing. So here are the different types of bonds that occur. You may recall that ionic bonding occurs when electrons transfer to reach stability for the individual atoms, and covalent bonding occurs when electrons are shared so that the individual atoms can achieve stability. And an example of that would be sodium chloride as an ionic bond versus chlorine gas, Cl2. So in sodium chloride, sodium has 1 valence electron, chlorine has 7 valence electrons. Stability for chlorine would be to fill that outer shell with a full 8 electrons, and stability for sodium would be to get rid of its lone third shell electron so that it could have a full 2 shell. So that electron will transfer from sodium to chlorine. That's going to make a sodium 1 plus and a chlorine 1 minus. And those opposite charges attract, and that's the bond, the attraction between opposite charges. In chlorine, on the other hand, chlorine has got 7 electrons, as we've seen. This other chlorine has got 7 electrons also. Neither one of them would be willing to give up an electron because there's no gain to giving up electrons. For chlorine, both for stability would need to gain an electron. So what they do instead is they approach each other and share their lone electrons to make a pair and thereby achieve stability for the two individual atoms. As two atoms approach one another, here we're looking at the very simple examples of two hydrogen atoms. There's a series of repulsions and attractions that occur. The repulsions are shown by the red arrows in this graphic here, and electrons are repelled by other electrons. So one hydrogen's electron repels the other hydrogen's electrons, and the two protons in the centers of these two atoms are repulsive to each other as well. However, there is an attraction between the electrons and protons, both within the atom and between atoms. As these atoms approach each other, the energy that's stored in the fact that the particles that are attracted to each other are now allowed to approach each other and not be held apart, that tends to lower the total amount of energy that's in the system. But then as they get closer and closer, the repulsive forces between proton and electron begin to increase the amount of energy that's stored. You can think of this almost like a spring. And there's one point at which the spring has the lowest energy storage, and that's when the spring is relaxed. If you squish it closer than that position, you store energy in the compression. And if you stretch it farther than that, you store energy in the extension of that spring. And this graph kind of illustrates that as well. As the electrons approach, as their internuclear distance gets shorter and shorter, energy drops because you're allowing the attractive particles to get closer to each other. But then once you go past a certain threshold, the repulsive forces take over, and then the energy begins to go back up. And there's one spot where that's minimized, and that's like the relaxed spring position. And that distance that those atoms are at when that lowest energy is achieved, that's called the internuclear distance, and that's the length of that bond. Now, that's not to say that those two atoms sit at exactly that distance away from each other. Instead, they oscillate back and forth. They vibrate a little bit because of the energy that they have. But on average, that's the length of that bond. Sometimes when electrons are shared by two atoms, the electrons that are shared are equally attracted to both of the nuclei in the two atoms that form the bond. So that means as the electrons are zipping around, thinking about them as particles, zipping around in constant randomish kind of motion, they pretty much spend equal time on both ends of the bond. So one end of the bond is just as negative as the other end of the bond. When that happens, this is called a nonpolar covalent bond. There are other times, though, when the shared electrons are not equally attracted to both nuclei. And so they spend more time on the one end of the bond that contains the nucleus that is the most attractive for the electrons in that bond. This means that, on average, over time, that end of the bond is more negative because the electrons are spending more time there. So we designate that with a little small Greek delta, lowercase Greek delta, with a minus, and the other side, a lowercase Greek delta with a plus. And we use those lowercase plus and minuses because it's not a full charge separation. It's just that one end is a little bit more negative, the other end is a little bit more positive. Such a bond is said to be a bond dipole or have a bond dipole, and we designate that with an arrow. The arrow points towards the negative end of the bond, and to kind of remind you, I guess, that that's the negative end of the bond, there's a plus sign on the tail of the arrow. Bonds like this are called polar covalent bonds. Now, they're covalent bonds because they're sharing valence electrons, covalent. But polar means they're not sharing them equally. One of the nuclei is more attractive for electrons, and so it kind of hogs the electrons on that end. There's this quantity characteristic of atoms called electronegativity, and it specifies the relative ability that the nucleus has to attract the shared electrons that are in that bond. That ability is tied to how big the effective nuclear charge is. The bigger it is, the more attractive it is for all electrons, including the shared electrons in bonds. So that means as we go towards the right-hand side of the table and the effective nuclear charges are increasing, we would expect to see increasing electronegativity. And the other thing that this will depend on is how close are those shared electrons going to be able to be to that nucleus. So that means smaller atoms would tend to be more electronegative when they're part of a bond. So that would lead us to believe that the farther up in a group, you would find more electronegativity. And sure enough, when you look at the overall trends, up in the upper right-hand corner, that's where we find the most electronegativity. And then as you move down and to the left, the electronegativity decreases. This actually is quantified by some numbers in the Pauling electronegativity scale. And this is a periodic table of electronegativities here. You can see that these range from 0 to 4. Nothing's actually 4, but that's the basic range. How do we tell if a bond is polar or nonpolar based on electronegativity? Well, if you think about a kind of a scale where higher electronegativity differences are on the left-hand side and lower electronegativity differences are on the right-hand side in this little scale, that blue zone represents electronegativity differences that are so big that we consider that the electrons have transferred, and those are ionic bonds. On the other end of the scale, you have electronegativity differences that are so small that we say that the electrons are pretty much equally shared by both ends of the bond, and those are nonpolar molecules. And in the middle, that's our covalent bonds that are not equal sharing. They're not so unequal that it's ionic, but there is a charge differential, and those are our polar bonds. What are the boundaries? Well, they're kind of fuzzy, but the boundary between ionic and polar is around 1.8, and the boundary between polar and nonpolar is around 0.5. There are other things that have to be considered, if you get really detailed about it, to determine if something is polar or nonpolar as a bond. But these are approximate boundaries, and we will mostly only look at cases where it's very clearly in the polar or nonpolar or ionic zone. And another way that we know that it's ionic is it's a metal and nonmetal. If it's a metal-nonmetal, that is definitely electron transfer. Let's look at some examples. An N-N bond. Well, here the electronegativity difference is 0 because it's nitrogen on both ends. So one electronegativity is the same as the other. There is no difference. So this is a completely nonpolar covalent bond. Here's another example, an NaF bond. Well, the electronegativity difference here is around 3. That's way over on the blue side. Also, sodium is a metal and fluorine is a nonmetal. And so both of those two factors will tell you that this is an ionic bond. This isn't a covalent bond at all. NH. Nitrogen is 3.04, hydrogen is 2.20. The electronegativity difference is about 0.8, and 0.8 puts you pretty much right in that green zone. So this is a polar covalent bond. CH bond. Carbon is 2.55, hydrogen is 2.20, The electronegativity difference is 0.3, and that's pretty clearly in the red zone. That's a nonpolar covalent bond. So we think of a CH bond as the electrons are pretty much equally shared between the carbon end and the hydrogen end. OH. Oxygen's 3.44, carbon's 2.20. The difference between those two is 1.2. 1.2 is right in that green zone. This is a polar covalent bond. This turns out to be a really important polar covalent bond, and in most of the instances throughout this class where you have to decide between polar and nonpolar, it's the presence of an OH bond that's going to help you make the decision. OH bonds are polar. Here's a CF bond. The electronegativity difference between 3.98, which is fluorine, and 2.55, which is carbon, is 1.5, and 1.5 is in that polar zone. As it turns out, anything that's covalently bonded to fluorine, in other words, any nonmetal bonded to fluorine, that's going to result in a polar bond because fluorine's electronegativity is much higher than any other electronegativity.